Welcome to Tech Talk here from Semicon West in California. I'm delighted to be joined by a group of guests this morning from a company called Terecircuits. I have to my extreme right Wayne Rickard, who's the CEO. Next to him is Jana Sheets, who's the Chief Technology Officer, and another board member who's also behind some of the technology here, of course, is my old friend and colleague Joe Felstad. So welcome, nice to see you everybody.
Welcome to Tech Talk with Trevor Galbraith, a video podcast that features industry leaders and experts from the electronics manufacturing community. Recorded at major events around the world and from the studios of Global SMT TV. Now here is your host, Trevor Galbraith.
Let's start with you, Jana. What is the background behind Terecircuits and where did it start? Where did it originate? And what's your vision?
Right. Thank you. Thank you very much, Trevor. So I think we could start with my thoughts toward the end of my time at HP Labs working on organic LEDs, where people wanted things to be flexible, but it really wasn't. And there was talk about flexible electronics. And I, with a background in organic chemistry and polymers, I thought polymer transistors were a great idea, but I learned that they just really weren't practical. And in fact, then I learned that you could make silicon very, very thin so that it becomes flexible and has a lot of the properties of what the people wanted from the polymer transistors. And you could make those thin pieces of silicon very small, and you'd still have thousands of transistors on them, which would be enough to do a lot of interesting things in the Internet of Things. But the question was, how would you handle them? A pick-and-place machine just didn't seem to be suited for that. And one thing and another led to this idea of how to use a polymer to do mass transfer of these thin, small devices from a source wafer to a substrate, positioning them using light in very, very precisely. So not being a business person, I didn't know really how to make a business out of that. And a number of years later, finally met Wayne, who figured out a good business model. So that's where it came from.
Great. Okay. So Wayne, maybe you can tell me you have two technologies that we're going to discuss today around the polymer transfer material. So the polymer material can transfer a number of components quickly, and then they release under the use of high-powered UV light. That is essentially what the patent's around. Is that correct?
Yes, that's correct. It's actually quite a flexible technology, so it can release thousands of components, hundreds of thousands of components in a single operation. So one of Jana's main insights was that you could take the technology that has the resolution of lithography, which we go down to nanometers, and you could apply it to semiconductor assembly. And the challenge there is that pick-and-place is a technology that's been around for 30, 40 years. Yeah. It's not known for being able to parallelize a lot of operations. An 8-head pick-and-place machine is state-of-the-art, whereas we can transfer thousands and thousands of components in a single operation. And we can do it with 1 micron of accuracy. So that type of placement accuracy, to do that with a pick-and-place machine, you actually have to slow the machine down because of mechanical settling time and positioning time.
Yes.
So this is an amazing approach. It solves a throughput problem, it solves an accuracy problem, and it actually solves, in some cases, a yield problem as well.
Right. So the application that I've seen you use or talk about is the transfer of LEDs. So it's all the same device, as it were. But what sort of volumes and transfer rates can you get?
So there's really no limit. The components themselves are about the size of a red blood cell. So you can imagine on a 4-inch epi wafer or a 6-inch epi wafer, you can get millions of tiny components on one wafer, and we're only limited by the mask that has apertures for where you want to release a chip. So it's possible to actually, in one operation, not just transfer the components, but do a pixel realignment. So in the case of a micro LED display, you've got a red, a green, and a blue pixel that have to be created.
Yeah.
And that's 3 different epi wafers and then 3 different mass transfers, and all with precise alignment.
Yeah.
But the pixel has a different pitch than the fabrication pitch. So by using a mask, we can actually transfer them at the pixel pitch.
The pixel pitch. That's really interesting. So, Jana, as I mentioned earlier with you, that this is a method of transferring these LEDs onto a substrate of some sort, but not interconnecting them. It's just a case of you're literally placing them there, and then the manufacturer can decide which way he's going to do it, whether he's going to connect with an epoxy or whether he's going to solder them or what he's going to do. Correct.
Yeah. So the in the case of what kind of interconnect technology could be, solder paste or solder bumps, or nowadays at the highest resolution one has thermocompression bonding. We have the ability within the process to control the amount of force that we bring those components down on, which is an advantage compared to laser ablation, which is a competitive process where there's really very little control. So we believe we'll be able to control that force so that almost no matter what the surface is, as long as it has any adhesivity at all, and even van der Waals attraction is a form of adhesion.
Do you know what level of force you can control on the Z height?
So that's still in progress, so I don't want to put a number on that. But
Okay. So you've got another process as well that you're using for system and package, where you're essentially using the same type of transfer process to transfer chiplets and materials into a package, which is solderless. Can you tell us a little bit about that?
Sure. So, and I'd say that as perhaps with many cases of a new technology, you have the low-hanging fruit, or the first things you can do that are easiest to introduce, and then there are the more complicated things. As far as that, the chemical process, the photochemical process that changes the polymer that creates a gas and a propulsion of a chip, it doesn't care whether it's an LED, a micro LED, or a 5x5 or 10x10 millimeter chip. It could be anything. The worlds that you sell into are very different. What we've discovered recently is that there are customers for particularly power electronics used in the automotive business, where they're using silicon carbide and gallium nitride, and those also have to be thin. There are various reasons why that's the case, heat thermal control and other reasons. And so their pick-and-place machines are breaking those chips. So even doing those transfers one at a time has a tremendous economic value. My idea, which I believe we'll get to eventually, is to make something called a system and package. So like the kind of thing that goes into a smartwatch today, for example. I think this is already a few years old. Apple's SiP had 30 different components inside this one package. So you could be making, hundreds, let's say 100 or 200 of those components, system and package, all at once. You place one chip in one microprocessor in each one of them, and you do that all in one second exposure. I mean, less than a 1 second exposure. And then you come along and you place the memory chips and so on. So you're doing this the advantages of the parallel processing also for system and package. And the chiplet world just only takes that to another level.
Right. No, you're right. I mean, the way, these die, they're thinning them all the time, and they're getting much more difficult to deal and to handle. I want to come to you, Joe, for a moment, because a lot of this technology is based around the original Occam principle that you had.
Let's put it this way, it's similar. Jana and I were of a common mind. It turns out, like a lot of things, innovation happens in lots of different areas. People see the same kinds of obvious, shall I say, put that in quotes, look at the way things ought to be. Jana was focused, it turns out, I gave a talk on the Occam concept back in like 2008, I think it was, in Florida at an SMTA event, and Jana approached me afterwards, and we just started chatting. She understood exactly what I was talking about, and I went, "Oh, great!" I don't have to explain it to her. Yeah. But her vision, is similar to what she just spoke of. Is that idea of what could be possible for the manufacture of electronics at a bigger level, writ large kind of things with chips and the like. I think some of the first efforts were up in Waterloo, Canada, where the intent was to see what might be done in terms of building RFID chips. And so, she had a good scope on how things get done. Of course, there's a lot of effort in that, and certain things happen in their own way. But to me, the beauty of it, the real beauty, and I don't know that came across as well, is the idea of being able to have an attachment material that disappears with light. It just goes to gas.
Vaporizes, yes.
Yeah,
yes.
so,
yes.
There's nothing to clean up.
Right.
It's done, and everything is right where it wants to be. And it's virtually untouched, so it's incredibly pristine.
Right.
Well, that same kind of thing is attractive to me. In fact, back when Jana asked me first to be an advisor to the company, I started looking at where are the opportunities in my space, where it might work. And one that struck me as an opportunity area would be pick and place of these discrete devices, which are, now you can put them in your pepper shaker, put them on your eggs in the morning and wouldn't know that you ate them. They're that tiny. And so, that ability to be able to place these things, create masses of them and then deliver them and then just drop the components where they're needed.
Right.
Right. And you never have to refill the tube, so to speak. So to me it was really, really attractive, and it remains attractive for the things that I've been talking about with Occam, which is
it must be. It's really exciting for you to see this idea coming to fruition.
Exactly.
And there's been a lot of people, as I said before we came on air, that really like the idea and have liked the idea for years, but we needed to see proof of concept. We need to see it actually working, and here we are coming to the point where we're actually.
Yeah, I think things that, everything has, it says, Victor Hugo said, nothing is more powerful than an idea as time has come. And I think that's still the case. We start to see things. The one thing that I think is going to be incredibly important for this in the world of chiplets, I wrote an article, I don't know, probably 10 years ago or more, talking about disintegrating ICs.
Right.
Break them down into IP blocks and then package them. And the key for me is, and it doesn't get a lot of talk, I've heard in recent times more talk around the idea of standards. But, going back to my days at Tesla where we first met many years ago, and we were both a lot younger.
You're showing my age.
So that, what we were focused on at Tesla was standards. In other words, being able to make the flip chip technology available to the common man.
Yes.
And, and you do that by, adopting a standard footprint and then letting things fall together. And so, when I put my little module together, if I will, with the help of my colleague, Vern Solberg, it's basically used Legos. I said, here, Vern, I'm going to go get you a bunch of Legos. Make a module for me.
Yeah. Well, I remember back in the early days, just to digress for a minute, these early days of Tessera, you were intending to be a manufacturing outfit. You toured me around the factory, and I remember you saying that's where the manufacturing is going to be. But after you got proof of concept, you literally turned into a licensing.
Well, we couldn't handle the world's volume. We were actually developing materials at the time, trying in our own in-house for silicones for the die attach to be able to create the buffer layer between the chip and the board. In other words, overcome the major flaw or failure mode in electronics is always a solder joint. So if you take the stress off the solder joint, then you have something that will work or should work nicely for a long time.
Okay.
So, but we went to Dow and asked them, to make something like this, and they said, sure, we can probably do that for you. How many carloads, tank carloads do you want? And we go, no, you don't understand. There's a value to this, and value proposition doesn't always register with large manufacturers.
Large organizations, yeah. Well, it's very exciting. So I want to turn back to Wayne for a minute, because Wayne, you came into the company about 4 years ago with obviously a strong business background as well to be able to help bring this thing to market. So where are we in terms of realizing the concept, getting into production, and getting licensing deals or whatever it is you're trying to do?
Well, I have a background in angel investing, and one of the concerns I had when I first met Jana was, wow, this is semiconductors had their day in the sun, but trying to get angel investors or even VCs to invest in a technology like this today, it's going to be a long road. We've been fortunate in that we've been able to raise $5 million over the course of the last 3 or 4 years. Yep. We've also received some government grants from the National Science Foundation. So we ended up with a pretty good source of seed funding. And we thought originally we might have to build a tool to support this process, which can be very capital intensive, and it's not really something you want to take on. But when we started looking at the environment, there were lots of competing approaches, lots of ideas. No big company had committed to building a tool that would support a laser-based transfer. Today, there's 8 separate companies that we're aware of that have laser-based tools that will all be compatible with our material. Okay. And what's exciting is that they've kind of put the cart ahead of the horse in a sense, because a tool company, they'll build a tool and they'll say, what's an off-the-shelf material that I can work with? But they found that all the off-the-shelf materials they use a lot of energy, they get ablated, and they leave residue. And we have a purpose-built material that's kind of met the crossroads of when the tools are ready and when the material's ready. Right. So we're working with, I would say, a majority of those companies now, and we're qualifying our material. A lot of those tools will work with our process and our material. And I think for us, it's been exciting because, number one, we don't have to build a tool. Yeah. And number two, they're attacking different verticals. So we have the micro LED opportunity that we mentioned earlier. There's some tool companies that are completely focused on that, and others are focused on semiconductor and pick and place replacement, and we have partners in that space as well. Right. So for us, it's all about now getting qualified and getting some pilot lines up and running. And it's, as you know, in the semiconductor world, nothing gets qualified overnight. It's going to take several more years of work, but we have the right partners, and it's looking very, very positive right now.
So you can't really give us a real timeline at this point, but
well, I can say that we did sign our first joint development agreement with a major semiconductor provider. Okay. And that timeline will be about a year. And at the end of that timeline, we'll be exiting with a tool partner that they've also identified and a process that works.
Excellent. Well, we'll look forward to that. We'll keep a close eye on it. Well, gentlemen and ladies, I want to thank you very much for coming in and telling us about this today. I'm excited for all of you, and especially for my old friend Joe here for actually realizing a dream. As I say, we'll keep a close eye going forward. But thank you for coming in today.
Thank you, Trevor. Appreciate it. Thank you.